Alright, we're out here on this misty morning to have a chat about circular motion. As you might have guessed, circular motion is all about things moving in circles. Like you, attached to a pole by a rope. You're running in a straight line, but because of that rope tying you to a pole, you don't move in a straight line. That rope holds you at a fixed radius from the pole. And so even though you try and run at a tangent to the circle, you still move in circular motion. That's because the tension inside the rope is providing a force at right angles to your motion. That force we call the centripetal force, center-seeking force, and we can calculate the size of how big that force needs to be by doing mass times velocity squared divided by radius. It's very important to notice that the velocity that you're moving at any point is a tangent to the circle, whilst the force is along the line of the radius to the circle, and that means that the force is at right angles to the velocity. The consequence of that is that that force can't change the size of the velocity, but we know that whenever a net force acts, and the net force is acting, there must be acceleration. That means the velocity must change. What's changing about velocity? It's a vector. What's changing is the direction of the velocity. At the top of the circle here, you're moving that way, then that way, at the bottom, this way, at the side, that way. And so your velocity as you move around the circle is constantly changing because of the centripetal force. And we call that velocity the tangential velocity, meaning the velocity at a tangent to the circle. And we can calculate how big it is. That equation's not on your formula sheet, so there's no red box around it. Vt is 2 pi r over t. That 2 pi r sounds familiar, doesn't it? Oh yeah, circumference of a circle, 2 pi r. What does that capital T mean? It means the period of motion, the time period, the amount of time it takes to completely repeat that motion. And so there is no such thing as the centripetal force. The centripetal force is just the name that we give to whatever force is holding us in circular motion. So if you're tied to a pole by a rope, then the tension force in the rope is holding you in circular motion. If you're the moon moving in circular motion around the earth, then it's the force of gravity that's providing the centripetal force. If you're a car going around a corner, then it's the friction between the car and the road that's pushing the car inwards. Now, that brings us to a very complicated point, which is that when you're inside the car and you go around a corner, you perceive as though you're being pushed towards the outside of the corner, and we talk about the centrifugal force. Now, it's a very good time to say that there is no such thing as the centrifugal force, and if that word is ever mentioned again, then it will lead to consequences that are diabolical. What is happening, the reason that you perceive that you're being pushed towards the outside of the corner when you're going around the corner, is in fact that the car is pushing on you to provide you with a centripetal force to make you go around the corner. And because we know that for every action force there's an equal and opposite reaction force, as the door of the car pushes you around the corner, you're pushing back against that. And it's that reaction force that you feel that makes you feel as though you're being pushed to the outside of the corner, even though anyone in a helicopter can see you're being definitely pushed towards the inside of the corner, because that's the way that you're moving. Let's have a go at this, see if we can do a problem. So, example, nearing the bottom of the hill, you approach Eureka Bend. You notice the sign recommending 15 kilometers per hour, mass of car 800 kilograms, radius of Eureka Bend I estimated at about 6 meters. Calculate the force that is provided by that contact between the car's wheels and the road. Remember, you're going to need to convert that 15 into meters per second first. You can pause the video now, make sure that you can get the correct answer. Hopefully things worked out for you like they did for me. I started by converting that 15 over 2 meters per second by dividing by 3.6, and I got 4.2 meters per second is the speed. Then I slapped the numbers into the equation. 800 times 4.2 squared over 6 came out with 2352 newtons. Quite a big force, really. It's the same as if you were trying to lift 230 kilograms. That's quite a big weight, quite a big force needed to push your car around that bend, even at that slow speed of 15 kilometers per hour. Now, imagine that partway around the bend you hit an oily patch left behind by a dodgy antique vehicle. I want you once again to pause the video and draw on the path that you think would be followed by the vehicle going around the corner as it passed over the oily patch and lost friction with the road. Now imagine that this is just a flat piece of road that's flat everywhere around it. You're looking down on it. Draw on the path that would be followed. Now hopefully you got something like that before we hit the oily patch, the friction was providing the centripetal force between the tyres and the road, therefore the car went round a circle, but once it hit the oily patch and lost friction, that meant that no net force acted, and therefore the car continued in a straight line at a tangent to the circle that it was moving around. Common mistakes are to draw the car going, hang on, we're going to do this in red pen, make sure that you know it's wrong. Red's the colour that's wrong. Commonly people might think that the car slides away from the corner, but that's not going to happen because there is no net force acting, and therefore it just moves in a straight line. That's Newton's first law. A body in motion will stay in motion at constant velocity when no net force acts.